My name is Patrick, as I said before. I'm a research engineer at Mistral, and very excited to be here for the talk. And yeah, first I want to say a bit about Mistral. So Mistral, I think we're Europe's leading AI company. We're focused on building efficient and open LLMs. I think one of the major differentiators to OpenAI maybe or Anthropic is that we try to be as open as we can while staying competitive. That means a lot of our weights are made openly accessible, or sometimes also fully open sourced with MIT licenses. We put a big focus on efficiency. So I think we're one of the first actually companies with our Mistral 7B V1 that really focus not only on super performant models, but also on really efficient and performant models. And we also take pride in being quite independent. So we try to work with every major player and not be mainly partnering with one big tech company. So I want to do a deep dive into model architectures in the LLM era, and also by doing so explaining a bit how we think about model architectures at Mistral, and in general a bit I guess like how people maybe should think about model architectures given the playing field nowadays. So I'm going to talk about essentially three of our main model architectures. One is just the standard LLM. The second one will be Mixtral, so a mixture of experts model architecture. And the last one, Pixtral, so which is a vision large language model that we released a couple of weeks ago. And then maybe in the end, I can also actually touch a bit upon the new Mistral models that we recently released with some fun interleaved attention mechanism. Cool. And yes, I think I said before, feel free to just ask me questions while I'm talking. Or you can put it in the chat, or I'm also happy if you interrupt me. But then also more than happy to answer anything afterwards. Great. Okay, to set the table a bit, I just want to give a bit an overview of the landscape today. And I would say that the most important aspect to consider when you train or build a large language model is to find the perfect trade-off between performance and efficiency. So that's mainly how we think about it at Mistral. And I think maybe these terms are a bit vague, so also to clarify them a bit more. By performance, I mean like, I guess like model capacity, and I also mean that you should try to find an architecture that has very good conversions when training, and is highly expressive, and also ideally is stable when training. And a lot of the components that I'll dive into later, that you probably all know, they relate very much. And also quite clearly is like the more weights you add to the model, the more capacity the model has, and usually the more performant it is. Cool. And then efficiency. So by efficiency, I guess people sometimes, people talk both about latency, throughput, and also memory. I think they're all a bit related nowadays. So what I really want to focus on here, and what I think is the most important aspect, is throughput nowadays. And I think that makes sense when you think about to what extent LLMs are already used in production. So I think I just copy pasted I think a Google link here that ChatGPT receives more than 10 million queries per day now. It's probably already outdated, but that should make it crystal clear that it's super important to be extremely efficient considering throughput, right? You want to be able to serve as many batches per second, or as many requests per second as possible. It's also important to not have a latency that is too high. So you also have to take into consideration that the user experience is reasonable, right? That you see the answer somewhat quickly. But I'd argue most of the time you want to optimize for throughput. I think it's also something that vLLM did extremely well when they came out. Right? It was a huge boost to throughput. The second thing that's very important is that the training time is, I actually wrote training time. I think what I really wanted to say is actually training costs. So I think training costs nowadays is very quickly amortized by inference cost. So the training cost is huge, but then running the model in inference afterwards is probably going to be a much bigger cost given how much usage LLMs have already. And the last important aspect is that requests usually are of very variable length, right? You can have requests that have a context window of hundreds of thousands of tokens nowadays, where you want to summarize something, or very short questions. So taking all this into account, this is, I guess, like how I define efficiency for inference. And then quickly going over the constraints, I think everybody knows that is, well, actually, one aspect I'm not sure that everybody knows it, but I think what's quite interesting is what is happening a bit in my understanding at the moment is that compute hardware advances a bit faster than networking hardware. What that means is that actually the mathematical operations, the math nodes, the flops, they increase a bit faster than you can actually transfer data between chips. And essentially what that means is also, in some sense, your memory is limited. So you have to also be careful with memory. You cannot just kind of have limited memory and only optimize for inference. Because if your memory if your memory requirement is too large, you're bottlenecked by networking speed eventually. I think that's something that's quite important to take into account when you design models nowadays. The second thing is also, very clearly, just hardware is very expensive. So try not to use too much of that. There's certain model sizes that are just completely unreasonable to train at the moment, given the cost of the hardware. And the last point is we also started adapting, I think, model architectures to hardware, because hardware, like the GPU chips, they take quite some time to build, to design, and then actually put into production. I think the cycle is around 2 years, I think. And that means that we want to adapt the model architecture for the chips, essentially. So it was maybe a bit of a long intro that most of you already know, but just to set the table a bit. So our goal is, again, to find the perfect trade-off between performance and efficiency. And now just a real quick recap of the transformers architecture that is the heart of, I think, every LLM nowadays. So what we have is we have input embeddings. So your input string is put into vectors, essentially. And then we stack transformer blocks. Transformers blocks, usually they're made of a norm to stabilize training. You have the attention mechanism to contextualize your input. Usually we have residual connections as well. Then the second part is the feed-forward layer, which in some sense adds a bit of, or allows the model to kind of add expressivity or transform the vectors in the way that's most useful for the model. And these components, they didn't change much actually since they came out, I think, in 2017 with attention is all you need. But I'll dive a bit deeper on how they're being changed and why they're being changed that way. And the last aspect that's very important is that inference is very different to training, right? Like training is you do a single forward pass for X input tokens. And in inference, you do a single forward pass for the input, but then you need N forward passes for the output usually. So there's autoregressive inference, right? And this is very different. Like that model architecture should be built probably in a way that optimizes this inference mechanism instead of maybe just the normal forward pass. And that's also where the KV cache is super important, right? Because when you do autoregressive inference, every request that you've already done is cached and can be reused. And then obviously we have page attention, which was a game changer in a way that the KV cache, the way I see it, actually page attention can realize that the cache plays a super important role, and it's super inefficient. And page attention really made it super efficient, so that you can serve many more queries. And to round it all up, the memory, I think nowadays is occupied by three things in inference. I'm talking about inference here only. The model weights, just the pure weights that you want to load into memory. The KV cache, that plays actually a big role nowadays. It can take up a huge chunk of your memory. And the last thing is the activation, which tends to take up less memory, but can also take up quite some memory given the model architecture. All right. So now let's dive a bit into the Mistral model architecture that I think is very similar to what other players also do. So we have multi-query attention. The one important aspect that essentially everybody does now is that you reduce the head dimension, or actually you reduce the number of heads of your KV projection matrices. So what that means is when you get the inputs here, and you pass it through your query, key, and value projection matrices, you actually, in a sense, have much fewer key and value projection matrices. You only have something like 8 heads. That means you have 8 projection matrices, whereas the query takes much larger number, which is 32. And the reason for this is that you can significantly reduce the KV cache. Remember this. That's quite important for inference, right? And it's something that matters less, I think, for training in that sense, because you don't really have a KV cache when you train. And yeah, when you even put this, or like when you make this more extreme, I think Noam Chazer actually, he in the first paper, he just used a single key value add. Then you have key value vectors that are 30 times smaller than the query matrix, and that's actually a huge difference. Your KV cache essentially is reduced by a factor of 32. The second thing is that the normalization there is very important for training. So you can stabilize training, you can stack more layers. So this part adds a bit to the performance of the model. And at Mistral, we use the RMS norm. I think people started off with the layer norm. I think people quickly realized is that you need some kind of normalization, otherwise your training blows up. And RMS norm is simply faster than layer norm. So let's just use the fast one and gives roughly the same results. The last aspect that I think is quite interesting is that most people don't use the standard, I guess like 2 feet forward, or I guess like 2 feet forward layer MLP anymore after the attention layer, but instead they use this gated linear unit or like with a switch activation function, or which is also called swig-glue, and it has a great conversions. So when you look at the training curves, it's super nice conversions, which means that the model adapts faster to your training data distribution. And this was also discovered, I think, by Noam, and he has a funny sentence in his paper. I think Noam also like wrote papers in the way he wanted to, without much review. And he just said like there's absolutely no explanation like why this works. It just works very well. And I think now it's pretty much used by everybody, actually, swig-glue, or by most models, I'd say. Then the last aspect that I think is maybe less known is that the vocab size also starts playing a huge role, actually, I believe. Maybe even a bit more in training than inference, but can also be in inference. And the reason is that the vocab size is quite large nowadays. I think Llama actually has a vocab size which is larger than 200K. And there you actually can have heavy activation memory cost under certain circumstances. And it's just like, I think if you do the math of having a very long sequence length, maybe something like 100K, and the very large vocab, you all of a sudden have a matrix in the end that is 100K times 200K in the case of Llama. And that might explode then very quickly. There's a lot of ways to go around this. There's things like, chunk. There's also why vLLM has chunk prefill. It's a super nice idea to kind of just split this huge memory into smaller chunks. But it's still, I think it's still quite important when you do things like, for example, when you want to retrieve the log props, right? Like you want to retrieve the log props of what you pass into vLLM, you can get out of memory quite quickly, and it's usually because of this, because your vocab size is huge. And then also in fine-tuning, it's also quite annoying, actually, to have such a big vocab size, because it can also blow up your memory, because there you kind of have to keep everything into memory for the activations. So at Mistral, we actually used for a very long time very, very small memory, very, very small vocab size of 32K, which is quite nice because you actually run into this problem. And now we also increased it to 128K, which is still, I think, quite small compared to Llama. But yeah, it's also larger now. What's important here is to realize this trade-off a bit, right? Like a large vocab size, everybody always thinks in the beginning, cool. Like you have more expressiveness, and also you need fewer tokens to say what you want to say, obviously. But the memory that does increase, and it can be quite relevant. Cool. All right, then let's go a bit into MOEs. I think Mixtral was quite a popular model when we released this, the 8x7, and I think also maybe the first actually publicly released mixture of expert model that was quite performant. And it's a really cool idea, right? Like the idea behind mixture of experts is, I think actually dates back a long time. I wasn't able to find the original paper, but I think there was a switch transformers paper by Google that popularized it again. And it's a cool idea in a sense that you want to heavily increase model capacity without hurting inference cost too much originally. So the idea is a bit that I guess like one angle you can look at it is a bit like people realize that having multiple attention heads is quite useful because different attention mechanisms can focus on different things. Then why not have multiple feed-forward layers in a sense, and different feed-forward layers can focus on different things. And the most important aspect then is that you actually don't need every feed-forward layer for inference. So what you do is you add some kind of routing mechanism. So what happens is that after you've done your multi-attention, that every token, so every token, every vector is passed through a routing, which is just like a linear layer with a softmax on top. And then this softmax decides which expert this token should see. So on the right side here, I think you can just see an example where you have the blue cat, and then for every layer, this token will see a different expert then, right? Like 2, 4, 1, 5 for the, and different experts for the other ones. The intuition here is a bit that I guess like what everybody says, the active parameters are much smaller because you don't need every expert. So it's a really cool idea. And also another thing is that you usually don't stack more layers on top of each other. So what you just do is like you add much more capacity to every layer. And that also means that you can be still pretty fast if you do a single query, because you only have to go through the same amount of layers. It's just that they might need to load more feed-forward layers into memory. But you can be still pretty fast when it comes to I guess like first time to token, or if you talk about just pure latency. So that's pretty cool. And I think it's still also a very interesting research path. I think people realize though also that sadly it's quite tough to have very good throughput with mixture of experts, because what happens with mixture of experts is that when you run a lot of queries, with the vLLM attention mechanism or like continuous batching, page attention, is you essentially need every expert anyways. If you run the binary requests all the time, so you just load them all the time to memory, and they're quite heavy, the models, right? So then the 8 times 7B essentially becomes the 56B. I mean, it's a bit less, but it's quite a big model then. Actually, it's 47 billion parameters. And then you take away a lot of space for the KV cache, and then you cannot serve as many requests anymore, and then your throughput suffers. So that's something to take into consideration. And yeah, one other aspect which is actually is even lower, if you go with more even lower level, is that mixture of experts, they have huge, well, I guess like the feed-forward is always the biggest matrix usually. And mixture of experts duplicates that, and you need to be able to load these matrices very quickly. And just purely like the loading time of these huge matrices takes a lot of time. So even by that, you tend to be bottlenecked quite often. It's not even so much that you take up so much memory. It can also just be like the time that CUDA takes to load these huge matrices kind of bottlenecks you. Yeah, I think the latest models, there weren't that many models lately that they use mixture of experts, but I think it's still a super interesting research path. And there's a lot of things we haven't figured out yet, and we need to explore and learn. Yeah, but maybe as a conclusion, I'd say like a hardware specs, I mean, I'd say favors a bit maybe the purely dense models at the moment, just because loading memory and shifting memory between devices is quite costly compared to just running the MetMill. Cool. Yeah, the last architecture I want to quickly touch upon is Pixtral. So it's I think it's a really cool model we released I think a month ago now roughly. Also Apache 2, so you can do whatever you want with it. And it's built on top of Mistral Nemo. Mistral Nemo. Mistral Nemo is a model we released before, also with Apache 2.0. And we added a VIT image embedding and used the mechanism that's quite similar to Llama. So where you essentially transform your image into image patches, and then you project every image patch into a text, or like, I mean, it's not a text embedding, but an embedding vector that you kind of treat as a text embedding. One very cool thing I think that we added here, oops, actually I want to go forward, is a 2D rope for the image embeddings. I think that's something that hasn't been done before, which made a lot of sense. Or maybe it has been done before, but I think not on the big visual language models that were released. And I think it's quite intuitive that it makes sense for images, right? Because you have, I guess, like 2 directions. So just kind of having 1D rope would mean that you kind of just go forward like in 1 row. 2D actually means that you kind of have the visual, like you cue the model with like the 2D coordinate system of it. Yeah, and I think in the paper there's actually some very nice graphs. We spent quite some time on trying to explain this. Well, so essentially is your image here is split into, here it's 12 patches, and every patch is given a or I guess like every patch has kind of like 2 angles, like one from the x-axis and the y-axis. So I see a theta 1,1 for the upper layer, and then theta 2,1, and then these ropey position embeddings are used for the pixel attention layers. And then afterwards it's very similar to Llama. I think there's some tweaks that are a bit different, but yeah, I think Llama also used the image break token. Yeah, then essentially you just treat the projected image patches as embeddings, and it works super well. Cool. Yeah, and then also, like, I think because we talked about model architecture, one thing that's very interesting with images is that images vary a lot in their size, right? You can have an image that is just 32 by 32 pixels that is still very valid, right? It's an important image that your model should recognize. But you can also have images that are huge. So like 2048 times 2048. And you do want to know every detail, right? I mean, if it's a map of something, you do want to understand what's actually on the image. And then you have to find a very good trade-off between the scaling down factor. If you wouldn't scale down these pixels to a smaller size at all, then you would just explode in memory. I mean, 2048 times 2048 image tokens. If every token, if every pixel will become 1 token, you have well over, I mean, it's actually well over a million tokens. So that's just, it's going to completely blow your memory. So in Pixtral, we use a scaling down factor by 16, but actually on both width and height. So you can kind of divide it by 256. So that means that a very big image like 2048 times 2048 is only 16K tokens, which is still quite a bit, I think. Yeah, and next we're probably going to scale this up as well. And yeah, just make a bigger model. Cool. Yeah, and then maybe to finish off the talk, I just want to highlight some of the things that I think we've done with vLLM. So we added kind of native model support now for all Mistral models in vLLM. We also released our models with vLLM now as like the kind of recommended way of running the models, because it's very efficient and just works very well. So there's this Mistral common library, which essentially takes care of everything, which is image processing and tokenization, and that's natively integrated into vLLM. So there's 2 options right now. You can either use the Hugging Face tokenizers or Mistral tokenizers. If you want to use Mistral tokenizers, you have to pass this tokenizer mode Mistral flag, which we recommend because we can kind of ensure that everything is correct in terms of tokenization. So if you run into weird results or tokenizations, could be worth just trying the tokenizer mode just to see if something is different. And also vLLM and also Mistral Common has very nice function calling support kind of out of the box. So if you do function calling, I'd also strongly recommend using the tokenizer mode Mistral flag. And yeah, and also I try to maintain the Mistral side of things. So the Mistral common side mainly of vLLM. So just ping me, Patrick from Platen, if you have any problems with Mistral models in vLLM and especially with Mistral common. And I added some links for tutorials. Yeah, and maybe just to is this very last point, we released Mistral models yesterday, a 3B and 8B. The 3B sadly we couldn't publicly release, And the 8D, I think, is a cool model because there's a new interleaved or racked attention, which means that we only use a full attention mechanism for every fourth layer. And the second, third, and fourth are capped to a sliding window of 32K. And this should give some very nice memory gains. I think at the moment there's still some work to be done with the efficient kernels, but also Llama 2 is a very similar, I think, design. But it's also, I think, quite an exciting way forward to see how much memory can be reduced by just not using the full attention on every layer. Cool, and I think that's it from my side. So I'll just hand over again to you, Michael.
So yeah, in terms of what's new for vLLM 0.6.3, we have a surprising amount of stuff. A lot of new models, some new text models. One thing I'll note is Mamba. That's been in the pipeline for a while in supporting a pure, SSM model. It was a big effort to get that over the line, and we're working on like future support for Mamba 2, which actually will be the Mamba Pixtral, I think is the best one out there that will take a crack at implementing from Mistral. And then, support for some more vision models like GLM, Molmo, and NVLM. Kind of exciting is like the first kind of reward model, explicit reward model supported from Platen 2.5. We're still figuring out the interface we want for this. This was essentially implemented basically as an embedding model. So if you're interested in reward modeling, very much recommend checking out that PR and checking out the RFC on how we want to define a reward modeling interface. And then also for there, we've been adding Llama 2 as an embedding model and expanding, particularly for a lot of vision language models, passing in direct input embeddings straight to the model input, expanding LoRa support to a lot of models, expanding pipeline parallelism to pretty much all the text models now and most of the embedding models. We've also been expanding bits and bytes quantization support for community requests. And then there's been good expansion on top of the base tool use support for the modern Llama models and intern-LM. And then finally, another thing with out-of-tree model integration and interface. So adding support for like out-of-tree embedding models as well. Basically, this means that kind of in like a Hugging Face Transformers way, you can essentially like inherit from this class and implement and register a new model to vLLM without needing to contribute code into vLLM. And actually a library or a model launch, I think named Aria, actually used this for the model launch to essentially allow people to run Aria inside of vLLM without needing to contribute the model yet. And then in terms of documentation, we have greatly improved the installation doc and better pointed people towards the like per commit wheels and Docker images, and a long-term feature request as we continually grow the list of features in vLLM. We want to be a little bit more honest about what features are supported with what other features. So I'll go into detail on what some of those are in the coming slide. And then in terms of hardware support, adding support for encoder-decoder models and cross-attention for CPUs. This has been sort of initial support. We still need to implement embedding model support for CPUs that we'll be working on. AWQ was also added to the CPU backend through the Intel's DNNL library. And then we've also been expanding some of the performance features that have landed over the last releases to XPU, like the async output processor, and better sampling support performance for AWS Neuron devices. And then in terms of architecture enhancements, obviously vLLM's kind of going through an architecture refactor right now. Definitely check out the pinned issues on how that's going and what some of the planned features are. There have been optimizations to spec decode, removing the slow batch expansion, fallback, block manager v2. It's finally the default. If you don't know what that means, just know that it means that prefix caching is going to be a lot more performant now and be supported with a lot more features, automatic prefix caching. And then also in terms of moving beam search out of the core, obviously in the previous release, we moved this to the offline LLM interface. Now it's on the OpenAI API server level. So, you using, those of you using beam search on the OpenAI API should now, see, not failures there and good performance if you're using prefix caching. Another thing with the torch compile support, as I mentioned, we'll go into that with detail on how that's going. And then there's been sort of repeated work on getting multi-step scheduling working with more features, so we can enable it by default and increase, really like throughput performance and reduce CPU overhead further. So hopefully in the next minor release, we hope to enable this by default. Those are most of the things. So I'll quickly cover the experimental full graph support with torch compile. This has been a long time coming that Kai Chao from UC Berkeley has really been driving with the PyTorch team. Basically, what we expose now is a environment variable called vLLM torch compile, and you can compile level, and you can set this to different numbers to signify how much of torch compilation you want to use. And basically, we have a guide if you want to start experimenting with this of trying your workload with different levels of compilation and letting us know if we have bugs in PyTorch. We've been reporting lots of bugs in PyTorch. PyTorch has been reporting lots of bugs in vLLM. So as we work through this, definitely if you want to give it a try and see if you can get some extra performance, particularly at the torch compile level 3 or 4. We do expect to see some performance improvements with this, particularly in latency use cases. But do beware, the compilation time is pretty severe right now, and we will resolve this, but it'll definitely take longer to compile than you're used to for just coup de graph compilation. Another thing I mentioned on the feature compatibility matrix, it's kind of ugly. We're working on the best way to represent it. But if you go to the docs page, there should be annotations on what all the different features are. And the goal here is to essentially give a cross product and show what features are compatible with what other features, so you can start to understand, if you want to use automatic prefix caching and that's a deal breaker for you, are you going to be able to use chunked prefill, or are you going to be able to use quantization or KB cache quantization or beam search or all these things. And then, of course, like on what different hardware levels are these things implemented or not implemented. Hopefully, this should help you start understanding what's implemented, what's not implemented. Also, many of the things that are not implemented have links on the X's, so you can see the tracking issue or known issue for this specific configuration not being supported. We want to keep this up to date and grow it. So if there's something that hasn't been reported yet or is an X without a link, definitely feel free to make issues and ask for this to be added to the matrix. And let us know if you want that, permutation of features to be supported. The priority is determined by the users like you. And that's basically it. We can get to questions now. And maybe since I'm the one talking, I kind of had a question directly for Patrick that I was interested in terms of Mistral. Maybe I'll just put the slides myself. So I'm kind of curious, since there's been, as you mentioned, Mistral has been, I think like the defining open source MOE model in terms of getting many libraries to support and take MOE seriously. Obviously, there's been a lot of MOEs since then from other model providers, and I'm just curious if if you had thoughts or concerns with maybe some of the patterns where some of had like shared experts, where there's sort of like mandatory experts that are always gone through on the MLP, or some of the models, I think like Arctic from Snowflake has like 64 or like 100, like a ridiculous amount of experts. and they're choosing, like a large number of them, or I think actually maybe a very small number of them. So I think in comparison to some of the other mixture of expert models that have come out, I think Mixtral is still a bit unique in that it's just, like a small number of experts and, only choosing 2 experts. So yeah, I mean, given what you said in terms of the performance concerns, like what are your consideration? What are your thoughts on some of the, other choices that?
Sure. Yeah, sure. So I think, first of all, I think it's a really cool architecture, and I think it's also a bit unexplored still. I think there's a lot of things we just don't know yet. In terms of, I think if you have too many mixtures, too many experts, it's you need to be. I mean, you have to have a very good training. I think paradigm, so that it doesn't get unstable or undertrained in any way, because the more experts you add, like the higher the chance of one expert being in some sense undertrained, or you don't have, it doesn't get enough capacity, and then you lose essentially all the capacity of the expert weights that you've added. I'm actually not an expert in Mistral, a mixture of experts, but from, I guess, like from my intuition, it's a bit it's not that easy to just I guess have more experts, right? You can always then say, well, your active number of parameters is much smaller the more experts you add, and you can maybe get a bit more performance. But then I think in reality, it's at the moment not really the case that if you have, let's say, like 32 or 16 experts, that you're much faster in inference compared to a model that is maybe of equal size but has fewer experts. And I think it's just much harder to have the very good stable training with more experts. So like that's one thing. And the other thing is what's also, I think where a lot of people play around with this, the top 2, kind of like how you force that, like what is your auxiliary loss, like to kind of put another loss, on the training that forces to use every expert. To what extent do you use the loss? Do you use it on every I guess like layer or not? I think there's a lot of things, like you can run ablations on and test, and I think things we haven't really figured out yet. In terms of shared experts, I don't know. Personally, I don't think it makes too much sense, because then like why not just like why use both experts? I guess, or maybe, or like, did you mean like sharing weights or?
No. Yeah, where you have essentially experts that are always chosen.
That are always chosen,
and like bypass the router. Yeah.
I gotcha. Yeah, actually, I haven't played around with this yet. I haven't really thought about this actually. But yeah, that could make a lot of sense, right? That would also give you more
for like kind of base knowledge, and then of course you have your specialized experts that are the ones you choose from. Intuitive.
Yeah. I think that's really cool. Yeah, I haven't thought about this too much. I know there's also a lot of work on. I think
translation
models anymore, but there was a lot of like one expert per language kind of thing for translation.
Oh sure, yeah.
But I think it's also like, I don't think it showed very clearly that the experts like tend to naturally do this, that they put all the knowledge of one language or like a one language group to some extent. But I think it's not worth to kind of enforce that natural like right away. And then in the case of translation, you can also argue then just why not trigger a different model upload completely when you have a certain language. But yeah, for me, the most interesting things is a bit, is I guess like the routing. It's like kind of like also how many experts do you choose? Mixtral does top 2, means you always have 2. And then for me, what's very interesting is I think like we still we're not close to like having very good, like we fully use all the capacity of the experts. I think what still happens quite a bit is that there's like some experts are a bit undertrained than others. And if you kind of prevent this heavily with auxiliary loss, then you restrain or restrict the model too much, I think, as well. So this is something I think we still haven't fully figured out yet.
Yeah, I see. Yeah. Makes sense. So there was actually a question in the comments of from a while back. Do you think rotary position embedding makes a significant difference? Obviously, in terms of Pixtral. I think yes, but I
think yes. I'd say yes. We've chosen it, and I think there's a good reason for it. So yeah, I think it makes. Also, I think it makes intuitive sense, and I think it just showed that it works much better for us in our ablations. So yeah, I think in general, I guess rotary embeddings are great. I think it's just such an, like, you know, like in the beginning, people used positional embeddings, right? And I think it's very clear nowadays that relative positional embeddings are much better. And to me, it makes sense to use 2D for image. And I think in our ablations, we've seen that it's better. So that's also why we've used it then.
Yeah. It's also much more like amenable towards like sequence like extension, right?
Exactly. Yeah. I mean, you're essentially limited anymore with sequencing, but everybody puts on like, been trained on like, I don't know, XK, but in the end of the day, you can obviously like pass longer sequences. There's nothing that like throws you. I mean, like actually, I think in vLLM actually initialized the whole KVA cache with a max length, but in a sense, I mean, you can also just kind of force a longer sequencing. The model is not going to go completely haywire. At some point, it's just not going to handle the context anymore. But the really cool thing I think about relative position embeddings is that you don't really have a restriction anymore on length. So I think it's quite cool.
Yeah. Actually,
right? Like that. Also, I think Llama 3.3 wasn't a release with an 8K, and people instantly did a 30K fine tune like a couple days later.
Yeah. I mean, I don't even think fine tunes. I think just like you know, like rope scaling configuration, just you know, just expanding it and see how it holds up. Was good enough for some community people. Yeah. Yeah. Okay. Let's see. Any other questions? Any value of training the mask? I'm not sure if training procedure was really shared for Mistral, but I haven't gone into the paper in depth. Or maybe it was the Pixtral paper that I'm remembering.
Yeah, I think we have a Pixtral paper for the smaller models. I think we haven't shared too much with the training procedure. I think I also cannot go too much into detail there, sadly. How they were trained.
Yeah, for sure. Any other questions from folks, either on Mistral or vLLM? I know another question I had was on, you know, something I've heard a lot from clients is like basically on model, you know, like multilingual support. I know like Mistral was one of the first to really like claim for that, at least, you know, at least in European languages. Do you have a strong idea of like keeping the like vocab like small, like really hurts like multilinguality? Obviously there's the data that the model is actually trained on, but do you think it really helps to have lots of unique tokens that are maybe specialized to certain languages? That helps a lot here, or do you think it's not necessary?
Yeah, I think it's a very good question. So I mean, in the beginning, we only focused on European languages at Mistral. I think in the beginning, actually, we only had 5 languages, and they just don't need a big vocab, because if they're all like European languages, share the same alphabet, I don't think it makes too much sense to have a large vocab. Also because of the reasons I said before, because it makes, I think, fine tuning actually quite hard, because if you find you're on long sequence length, then you tend to run into out of memory errors. And I think a lot of people also release this kind of compression factor, and now for different languages. So I think even like OpenAI tokenizer, right? I think you can actually look at it, and you can kind of compute like compression factors, right? Like you take a certain language, you run the tokenizer on it, and then you kind of can see how much kind of bytes of this language you can compress into how many tokens. So I think there's like things like compression factors per language. And I think if you want to include all languages, including like different alphabets, then I think, yeah, you probably need a bigger vocab size. But it's always like a trade-off, I think. Yeah, and I mean, I think, for example, if you only do European languages, I think you don't have to have I think honestly a 30K is good enough. Like, I don't see a reason why. And the end of the day, it's all like Unicode, right? Like in the end, these tokens are trained on Unicode. And I think if you don't have too many different Unicode characters in your training, then, I mean, if you only use the alphabet, then you don't have actually too many different Unicode numbers that you have to take care about, and then you don't need that many tokens, I think. And I think it's quite nice to have a small vocab. Actually, you actually can run very long sequence lengths without memory problems. Yeah, maybe one aspect I think is also quite interesting to think about is when you looked a bit at the Llama 2 release. I think they released this did they release a 27B as well? Yeah, I think so, no? 27B, 9B, and
like
2B.
Yeah,
2B, and I think and so they all share the same vocab size, right?
Yes, yeah, but the attention was different on the larger ones. I remember.
Okay.
I think it was definitely the 27B, maybe the 9B had the soft capping.
Yeah.
I remember this because in VLM, we only supported at the time soft cap with flashes for a backend, so we had to have a warning about to properly support running with flash infer.
Yeah, but I think for example 2B with the 200K vocab size is quite big. So that's something that matters, right? For such a small model, such a large vocab size is actually can relevant. And I guess something that's quite obvious is when you I think Llama was distilled, and then when a lot of people do distillation also nowadays, when you distill, you tend to keep the same vocab size. Where the problem is when you have to keep a 200K vocab size for such a small model, it's a bit it's not great, I think. So that's also something I think that's very interesting to think about a bit how to deal with this. Because for a large model, it's fine to have such a big vocab size, for a 100B model, but then for 2,
yeah. I mean, I think we definitely notice it every model release because of our focus on quantization, mostly on the linear layers, right? And so for instance, Llama 8B, right? Even that, the LM head in the embedding is about 1 billion parameters because of the size of the vocabulary and hidden size that. So if you compress everything to 4 bits, you're still spending 2 gigabytes essentially for bfloat 16 embeddings in LM head. So it's but if you spend the work to quantize the embeddings, you're not really saving much performance. You're really just optimizing for memory, and then do you really need to save memory that much? But definitely in terms of the activation size, it can certainly be the difference of activations fitting into cache or not, between layers. I definitely agree. Both the size of the tokenizer and the size of the hidden size of the model. Pretty important for performance. So I think we're basically at the end here. So let me just get through the final things. So definitely feel, we're happy to have you here, and we want you to grow your contribution to VLM. So if you're interested in any of the features we talked about here, make sure to search in the issues for them or look for the good first issue tags. We have several RFCs where we talk openly about the progress on lots of these features. So, be active on GitHub, ask questions, let us know what's going on. As always, give us feedback on office hours or in the Slack and community on what VLM can do better to, help serve your needs or help answer your questions. We'll be at a few events upcoming. The most recent one will be NeurUps in December, where we'll be Neural Magic will certainly be there, and some folks from VLM will have stickers if you want them for VLM. Neural Magic will be giving a webinar at the end of this month on how we help enterprises with VLM. And of course, if you want to work on VLM, we're always hiring more engineers at Neural Magic. And that's basically it. Thanks everyone for joining in. Thanks, Patrick, for the great presentation. As we mentioned before, the recording will be shared afterwards, probably next week. So you can share around your communities and companies. And that's basically it.
Cool. Thanks a lot for having me.
Yeah, thanks, Mike. Thanks a lot.
Thank you.
Take care, everyone.